In our previous video, we learned that the Cartesian plane is another word for the x and y axis. A point at which the axes meet is known as the origin and has coordinates 0, 0. Let's put a black dot on our diagram to show the origin over here. Now, any point in the Cartesian plane has an x coordinate and a y coordinate, but whether these coordinates are positive or negative depends on where they lie in the Cartesian plane. Along the x-axis, we can see that x values to the left of the origin are negative and x values to the right of the origin are positive. This applies to y values as well. Y coordinates above the origin are positive and below the origin are negative. The Cartesian plane is divided into 4 sections. We call these quadrants, and we can name them quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Quadrant 1 is to the right of the origin, so the x-coordinate of any point in this quadrant will be positive. It is above the origin, so any point in this quadrant will have a positive y-coordinate as well. So any point in quadrant 1 will have the coordinates x, y. Quadrant 2 is to the left of the origin, so any point in this quadrant will have a negative x coordinate, but the quadrant is still above the origin, so our y coordinate will still be positive. This means that any point in this quadrant will have the coordinates negative x, positive y. Quadrant 3 is also to the left of the origin, so the x-coordinate of any point in this quadrant will be negative. It is also below the origin, so the y-coordinate of any point will be negative as well. So any point in this quadrant will have the coordinates negative x, negative y. Finally, quadrant 4 is to the right of the origin, so our x-coordinate is positive, but below the origin, which means our y-coordinate is negative. So any point in quadrant 4 will have coordinates positive x and negative y. In our previous video, we said that when working with trigonometric ratios in the Cartesian plane, sine theta is equal to y over r, cos theta is equal to x over r, and tan theta is equal to y over x, where x and y are the coordinates of a given point. The value of r is always positive. It doesn't matter what quadrant the point lies in, but we can see that the different quadrants determine if x and y are positive or negative. This means that the different quadrants will determine if the trigonometric ratios are positive or negative as well. In quadrant 1, we already know that sine theta is equal to y over r, cosine theta is equal to x over r, and tan theta is equal to y over x. All of our ratios are positive if we are working with an angle in quadrant 1. In quadrant 2, the x-coordinate is negative and the y-coordinate is positive. So here, sine theta is equal to y over r, cos theta is equal to negative x over r, and tan theta is equal to y over negative x. Sine theta is the only ratio that is positive, as cos and tan are now both negative. In quadrant 3, both the x and y coordinates are negative, so now sine theta is equal to negative y over r, cos theta is equal to negative x over r, and tan theta is equal to negative y over negative x. But remember that if you have a fraction with a negative value in the numerator and a negative value in the denominator, the negatives cancel each other out, and we are left with a positive value. Tan theta is equal to negative y over negative x. The negatives cancel out, and we see that tan theta is equal to y over x. From this, we can see that in quadrant 3, sine theta and cos theta are negative, but only tan is positive. In quadrant 4, the x-coordinate is positive, but the y-coordinate is negative. So now, sine theta is equal to negative y over r, cos theta is equal to x over r, and tan theta is equal to negative y over x. In this quadrant, cos theta is the only positive ratio, as sine theta and tan theta are now both negative. To help us remember which ratio is positive in each quadrant, we use what we call the cast method, C-A-S-T. In quadrant 4, only cosine is positive. In quadrant 1, all the ratios are positive. In quadrant 2, only sine is positive. And in quadrant 3, only tan is positive. Please make sure that you learn this. Let's tidy this up, and we can look at different angles. In our previous video, we said that when drawing in angles, we start on the x-axis at 0 degrees to the right of the origin, and we move in anti-clockwise direction. Each quadrant takes up 90 degrees. So from the x-axis to the y-axis is 90 degrees. This means that if the terminal arm lies in the first quadrant, the angle it creates will be an acute angle, as it is less than 90 degrees. If we keep drawing our angle from the first quadrant to the end of the second quadrant, we now have 180 degrees. If the terminal arm lies in the second quadrant, we are working with an obtuse angle, because an obtuse angle is greater than 90 degrees, but smaller than 180. Finally, if we keep drawing our angle from the second quadrant back down to the y-axis, our angle will be 270 degrees. And if we keep drawing further back to where we started, we have a full rotation of 360 degrees. An angle that is greater than 180 degrees, but smaller than 360, is known as a reflex angle, and our terminal arm will lie in quadrant 3 or in quadrant 4. Now, just because we have drawn all the way back up to where we started, it does not mean we have to stop. We can keep going around and around as many times as we want. So you may see questions that considers angles greater than 360 degrees. As an example, let's look at where the terminal arm will lie if we are considering an angle of 400 degrees. We know that a full rotation is 360. So if we are considering 400 degrees, what is left? So we can say 400 minus 360 degrees, and we get an answer of 40 degrees. So from the x-axis, we still need an angle of 40 degrees. 40 degrees is less than 90 degrees, so our terminal arm will lie in the first quadrant. Now that we have this information, let's look at how we work with trigonometric ratios in the different quadrants. Before we do this, let's quickly tidy up our page, put in our numbers and our x and y coordinates. Now we can look at some examples. In which quadrant is the terminal arm of angle theta if it passes through the point 5, -2? In this case, x is positive. In the diagram, the value of x is positive to the right of our origin. So our point could be in quadrant 1 or in quadrant 4. But y is negative, so we are looking at y values below the origin. Quadrant 4 is the only quadrant where x is positive and y is negative. So we can write quadrant 4 as our answer. Let's do another one. In which quadrant is the arm of angle theta in the standard position if theta is equal to 140 degrees. Now, we know that quadrant 1 only considers angles smaller than 90 degrees. So theta cannot fall into quadrant 1. Let's put an X in over here. 140 degrees is greater than 90. So our terminal arm will not fall into quadrant 1. But what about our other quadrants? Let's look at the other side of the x-axis. 140 degrees is smaller than 180. So the terminal arm will lie on this side of the x-axis. From this, we can see the terminal arm has to lie in quadrant 2. Draw a sketch to show angle theta in the standard position if theta is equal to 200 degrees. Let's tidy this up so we can focus on our angles. Now, 200 degrees is greater than 180 degrees, so our terminal arm will lie below the x-axis. But 200 degrees is smaller than 270 degrees, so it needs to lie to the left of the y-axis. This means that we can draw our terminal arm in the third quadrant. Let's draw in our angle, and now we have completed this question. Let's do another example. State in which quadrants the terminal arm of angle theta is if sine theta is smaller than 0. To make this a bit easier for us, let's put our cast system back into the diagram. Remember that only cosine is positive in quadrant 4, all the ratios are positive in quadrant 1, only sine is positive in quadrant 2, and only tan is positive in quadrant 3. If sine theta is smaller than 0, we are looking for the quadrants where sine is negative. All the ratios are positive in quadrant 1, and sine is positive in quadrant 2. This means that sine must be negative in quadrant 3 and in quadrant 4. State in which quadrant the terminal arm of angle theta is if cos theta is greater than 0. If cos theta is greater than 0, we are looking for quadrants where cos is positive. All the ratios are positive in quadrant 1, so cos theta is positive here. And from cast, we can see that cos is also positive in quadrant 4. In this case, we are looking for the position of the terminal arm if sine theta is equal to 1/3. Now, to solve this question, you do not need to use 1 and 3 to figure out where the terminal arm lies. All we need to do is determine if sine theta is positive or negative. Sine theta is equal to 1/3, so sine theta is positive. All ratios are positive in quadrant 1, so sine theta is positive in quadrant 1. And from cast, we can see sine theta is also positive in quadrant 2. Let's do another one. Find the position of the terminal arm if tan theta is equal to -1.5. Here, all we need to do is focus on the fact that tan theta is negative. This will tell us where the terminal arm could lie. All ratios are positive in quadrant 1, so our arm cannot lie here. Sine is the only positive ratio in quadrant 2, which means that tan theta must be negative, so our terminal arm could lie in quadrant 2. From cast, we know that tan theta is positive in quadrant 3, so it can't be this one. In quadrant 4, cos theta is the only positive ratio, which means that tan theta must be negative in quadrant 4 as well. Now let's look at an example that's a little bit more intricate. Determine the function value of the given angle and state in which quadrant the terminal arm lies. And we're given the equation 3 sine theta plus 1 is equal to 0. In this case, the function is sine theta. So to find its value, all we have to do is get sine on one side of the equal sign. Let's start by moving the 1 across, and we get 3 sine theta is equal to -1. Now, to get sine by itself, we need to divide both sides by 3. And on the left, we now have sine theta is equal to -1 over 3. We can now see that sine theta is negative. From cast, we can see that sine is negative in the third and fourth quadrants. Let's do another one. In this case, we have the equation 1 over 2 tan 2 theta minus 1 is equal to 0. And we need to find the quadrant where the terminal arm lies. So let's start by getting the ratio tan 2 theta by itself. Let's move 1 across, and we now have 1 over 2 tan 2 theta is equal to 1. Next, we need to get rid of the fraction 1 over 2. And we can do this by multiplying both sides by 2. And we end up with tan 2 theta is equal to 1 multiplied by 2, which is 2. Now, please don't worry about the 2 theta. For this question, our aim was to get tan theta by itself. And now we have done this. The trigonometric ratio tan is equal to 2, which means it is positive. So all we have to do now is determine where the terminal arm lies. Tan is positive, and all ratios are positive in quadrant 1. So our terminal arm could lie in quadrant 1. We also know that tan theta is positive in quadrant 3, so our arm could lie here as well. Let's make some space and look at some more examples. Calculate the value of x, y, or r. For part A, we are given this diagram, and here we need to find the value of x. Remember that in quadrant 1, both the x and y coordinates will be positive. In quadrant 2, x is negative but y is positive. In quadrant 3, both x and y are negative. And in quadrant 4, x is positive but y is negative. The value of r will always be positive, regardless of which quadrant the terminal arm lies in. The question tells us the length of the terminal arm is 5 units long. So we can make a note of this over here. It is our r value. So we can say r is equal to 5. It also shows us that the y coordinate of the given point is 3. So we can say y is equal to 3. Now we have the value of r and the value of y. So we can use Pythagoras to find the value of x. And we can now say x is equal to r squared minus y squared, all under a square root. Now we can fill in our values. We can say x is equal to the value of r, 5 squared, minus the value of y, 3 squared, all under a square root. Now we can take our calculator. We can say 5 squared minus 3 squared is equal to 16. Square root our answer, and we get 4. But remember that the root of a value could be positive or negative, which means x could be equal to positive or negative 4. Now we need to look at our quadrant to determine the actual value of x. Our point lies in quadrant 2, and in this quadrant, the x coordinate is always negative, which means that x is equal to negative 4. Let's do another example. In this case, we need to solve for y. Let's start with the information we've been given. The diagram shows us the terminal arm is 13 units long. This is our r value, so we can make a note, and we say r is equal to 13. It also tells us the x coordinate of the point is 5. So up here, we can say x is equal to 5. Now we have the value of r and the value of x, and we can use Pythagoras to solve for y. Let's make y the subject of the formula, and we say y is equal to r squared minus x squared, all under a square root. Now we can fill in our values. And we say y is equal to the value of r, 13 squared, minus the value of x, which is 5 squared, all under a square root. Now we can take our calculator. We say 13 squared minus 5 squared is equal to 144. Square root our answer, and we get 12. But again, a root can be positive or negative, which means y can be positive or negative 12. So let's look at our quadrant. The point lies in quadrant 4, and in this quadrant, y is always negative. So in this case, y will be equal to negative 12. Let's do another one. B is a point in the Cartesian plane. Determine A, OB, B, cos beta, cosec beta, and tan beta. Let's start with part A. The length of OB is the length of the terminal arm from the origin to point B. On the Cartesian plane, this is our R value. So let's start with the information the question gives us. The terminal arm lies in the fourth quadrant, and point B has coordinates 1, negative 3. So in this case, x is equal to 1, and y is equal to negative 3. With values for x and for y, we can use Pythagoras to find the value of r. So we can now say r is equal to x squared plus y squared, all under a square root. Now we can fill in our values. So we say r is equal to the value of x, which is 1, squared, plus the value of y, which is negative 3. Let's put it into a bracket, squared, all under square root. Now we can square our terms. 1 squared is still 1, plus negative 3 squared, which gives us 9, all under square root. Finally, 1 plus 9 gives us 10. So we get an answer of root 10. Remember that it doesn't matter which quadrant the terminal arm lies in. R will always be positive. So let's make a note of R up here, tidy this up, and now we can move on to part B. Determine the value of cos beta. We know that sine theta is equal to y over r, cos theta is equal to x over r, and tan theta is equal to y over x. Cos theta is equal to x over r. So in this case, x is 1 and r is equal to root 10. So now we can say cos, in this case our angle is beta, is equal to x, which is 1, over the value of r, which is root 10. This is our answer. Now we can move on to part C. Determine cosec beta. Cosec theta is the reciprocal ratio of sine theta. Sine theta is equal to y over r, which means that cosec theta is equal to r over y. Here r is root 10 and y is equal to negative 3. So now we can write our ratio as cosec, our angle, which in this case is beta, is equal to the value of r, root 10, over the value of y, which is negative 3. Let's move on to part D. Determine the value of tan beta. We know that tan theta is equal to y over x. So in this case, y is negative 3 and x is 1. So now we can say tan beta is equal to y, which is negative 3, over x, which is 1. Any fraction over 1 leaves us with the numerator of the fraction, so tan b is equal to negative 3. Let's do one last example. Theta is an angle in the third quadrant, and k is the point negative 5y. OK is 13 units long. determine A, the value of y, and B, tan squared theta plus 1 is equal to sec squared theta. OK is the length of the terminal arm from the origin to point K. This length is our r value. So let's make note of it up here. And we can say r is equal to 13. And let's put this on our diagram as well. Now we can start with part A. Here we need to solve for y. We know that r is 13. And on the diagram, we can see that x is equal to -5. So let's make a note of this as well. Now we have enough information to use Pythagoras to solve for y. So we can say y is equal to r squared minus x squared, all under a square root. Now we can fill in our values. Y is equal to the value of r, 13, squared, minus the value of x, -5, let's put into a bracket, squared, all under a square root. Now we can take our calculator, and we say 13 squared minus, let's put -5 into a bracket, squared is equal to 144, square root our answer, and we get 12. But again, a root can be positive or negative. Our terminal arm lies in quadrant 3, and in this quadrant, the y-coordinate is always negative. So in this case, y is equal to -12. Let's make a note of it over here. Now we can tidy this up and move on to part B. Here we have to solve the equation tan squared theta plus 1 is equal to sec squared theta. Let's start by writing down our trigonometric ratios for sine, cos, and tan. Now, to solve this equation, all we have to do is prove whether or not the left-hand side is equal to the right-hand side. Now, you can start with either side, but it may be easier to start with the simpler side. The right-hand side only has one term, so let's start here. To show we are solving the right-hand side, we write RHS for right-hand side. Now, sec theta is the reciprocal ratio of cos theta. We know that cos theta is equal to x over r, which means that sec theta is equal to r over x. In this case, r is 13 and x is -5. So we can say sec theta is equal to the value of r, 13, over the value of x, which is -5. But in this case, we need to square sec theta. So let's put a square in over here. Let's put a bracket around our fraction and square it as well. Now we can simplify. 13 squared gives us 169 over -5 squared, which is 25. This is the value of sec squared theta. It is also the value of the right-hand side of the equation. So let's make some space. And under RHS, we can write sec squared theta is equal to 169 over 25. Now we can look at the left-hand side of the equation. Let's make a note, and we say LHS for left-hand side. Here we have tan squared theta plus 1. Let's start with tan theta. We know that tan theta is equal to y over x. And in this case, y is -12 and x is -5. So we can say tan theta is equal to y, -12, over x, which is -5. Now, remember that when you have a fraction with a negative value in both the numerator and the denominator, the negatives will cancel each other out, and we're left with 12 over 5. Here we are looking at tan squared theta, so we need to square our fraction. So let's write 12 over 5, put it into a bracket, and square it. We are looking at the value of tan squared theta plus 1. So we can say plus 1. Now we can square our bracket. 12 squared gives us 144 over 5 squared, which is 25. Now we need to add 1 to this fraction, but it is always easier to add a value with the same denominator. Any fraction with a numerator and denominator have the same value is equal to 1. So our first fraction has a denominator of 25. So let's change 1 into 25 over 25, and we can write it over here. Now we can add our fractions together. 144 plus 25 gives us 169 over our common denominator of 25. Now we can see that the left-hand side and the right-hand side of the equation are both equal to 169 over 25, which means that both sides of the equation are equal. So, as our final answer, we can say the left-hand side is equal to the right-hand side. And we have now completed this question.